So, yeah, today I will speak about something on the lithium-ion batteries, and I hope that there is not much talk on the battery, so I should be especially for the students that how the battery works and what are the basic principles. So yeah, this is for those who knows all these things. So this is for a recapitulation. So and the battery is basically mostly dominated by the chemist people, but also from the condensed matter point of view we could do a lot of work, and that we try to do today, and I will try to emphasize towards more getting close the nucleus, so by doing the exact simulation. But before that, so basically what we have in the this one is the conventional lithium-ion battery that we have almost in our mobile phones and laptops. So we have basically a lithium cobalt oxide, which is a spinel kind of structure. So there is lithium is the alkali metal, and that cobalt is the 3D transition metal, and that is oxide. So and also different 3D transition metals is applied, but lithium cobalt oxide was mostly successful, and it was commercialized in 1991 by the Sony battery. And there is a two-dimensional element which is used as a anode material. So we have a cathode and anode, and in between there is a electrolyte. That is the first generation lithium battery. There people use something lithium polymer with lithium based ionic liquids in the polar non-polar solvents. So basically what happens, we have basically charging and discharging. So that means like when we draw power from the outer circuit as per our interest. So lithium basically goes from the cathode side to the anode side, and during discharging this lithium should come back to the anode side, and this should be a recycle way, and then we get that is called like cyclicity. And the important part is that when we do this kind of charging discharging, because of the charge transfer, that material should not degrade, and this getting and coming back is called the intercalation process. So when lithium goes back from lithium to the this graphitic carbon, so there it is called lithium is deintercalated, and when lithium comes back here, so it is called intercalation. So here in respect of lithium cobalt oxide, when lithium goes here, this is called the intercalation, and here at that moment it is called deintercalation. But there, because of the lithium ion goes from here, so there you could see there is a change in the oxidation state of the transition metal, and that's why people use 3D transition metal, because there are a lot of different variable transition state is available for the 3D transition metals. And there is also something like used people like is for thin film batteries, but the thing is like there is very thin kind of lithium metal is used, but there is a issue of safety. So there is a safety issue for this case and this case as well, and there are a lot of incident happen. So people think about in terms of all the cathode, anode and electrolyte in the solid form. So for example, when we have the solid electrolytes that I am going to talk today, it is on the Li3INCl6 lithium indium chloride. This is a halide system. So there basically we have this kind of lithium cobalt oxide at the cathode, and anode is also something lithium indium alloy or some any kind of materials in the two-dimensional sense. And there are this kind of additives are there, but I am not going to talk about today because they are basically trying to make good addition kind of thing. So basically people think about that solid electrolytes, so they should have the comparable conductivity that people already have for the liquid electrolyte. And now this is the schematically what we see, that is a 3D transition metal, and this is a layered kind of thing. So lithium ion goes from here and sit on the anode part, and then it comes back. But why is important from the, for example, from condensed matter point of view, because this is understood that here we have the lithium as a anode, if we consider that, or we could think about the graphene like thing. So there's the Fermi level for the both cases almost in the same level, and then we have the 3D transition metal, and there this is the maximum available states for, below the Fermi level. So for example, this is the cobalt. So when we have the 3+ to 4+ hopping, for the 3D transition metal. So this is the position. Schematically it is understood like this will be in this position and then lithium will be here. So that means the difference gives me the electrochemical potential. And we could see that when we move from lithium cobalt oxide to lithium nickel oxide, lithium manganese oxide, and so on and so forth. So we can have sometimes a higher difference, that means it gives higher electrochemical potential, but also you could have like something lowered kind of thing that we can see like for lithium manganese oxide and lithium nickel oxide. And the first lithium cathode was used as titanium disulfide, which was lithiated there, and the first lithium battery it came around 2.4 volt, and that is understood because the level of the maximum occupied over the sulfide and the titanium, and the gap is quite smaller than lithium cobalt oxide. Now so we understood that cobalt could be a promising material for from the cathode point of view, but the thing is like if we even change the symmetry, for example we could think about that the same redox part Fe2 plus in the different kind of crystal systems. For example, you could see Fe2O3, Fe2Mn, MO4, and then Fe2SO4. So these kind of different crystal structures also, the same redox pair is the structural integrity is so different that we could have the higher potential, and that means basically the Fermi level of the maximum occupied part of the redox part is quite bigger. So in that way, if we could think about only one redox part, but we change the different structures, we could go for the higher electrochemical potentials. Now this is the cathode part, but for solid electrolyte part or the electrolyte, that is also understood in terms of the band that is shown here. So basically we have, as I mentioned, we have the cathode and anode. Now the anode is basically we have a metallic system. So the electrolyte, this is the, if we consider this is a polymer kind of material, so that means there will be a HOMO-LUMO gap. So the maximum value of the position of the LUMO, it should be higher enough to the chemical potential of the anode, and this is the work function of the anode. And similarly the lower part of the LUMO should be at least matching with the cathode chemical potential. So this is because to prevent the material when we have the charge transfer that we have seen here, to have this stability. And of course if we have some situation that the level is not exactly like that, but it should be higher, then there will be a formation of mixed phasic, is a biphasic or different kind of phases are there. So that is called ACI layer, and that happens both in cathode and the electrolyte. So basically these kind of things we cannot avoid, but that is the natural part that we have, and that has sometimes positive thing and negative, positive effect and negative effect as well. And the important part is like when we see the that material, so basically the electrolyte are basically is a ionically conducting, but the thing is that they have wide band gap material. They are basically a semiconductor, not semiconductor, it's an insulator material, and at least they have a band gap of the like more than 4 electron volt or 6 electron volt, but the cathode is of the order of 0.5 or 0.6, something like that. But there is one important point that the position of this HOMO-LUMO gap is mostly important. So for example, if we have any wide band gap material, it cannot be suited as a anode with any kind of cathode or anode. Otherwise water can be used as a electrolyte in the sodium-ion battery. So we need to think about that what is the particular Fermi level position for both cases. So there was this concept was modified in later on, but overall this is the idea. So in terms of the solid electrolytes, as mostly people think about from the safety point of view, so there are different kind of materials that people have used. So there is polymer solid electrolytes, and there are also gel polymer based solid electrolytes and hybrid polymer electrolytes, and also there are oxide based solid electrolytes like LLZO, something like lithium zirconium oxide, and also these hybrid solid electrolytes. And so basically most of them are have both pros and cons, because we could see that mostly the halide solid electrolyte, if we think about, they are not very much stable in the static air, but the lithium indium oxide that we have studied in this presentation, that is stable in the room temperature and as well as the normal air. So like for example lithium yttrium chloride, it is somehow here. So that is also show a better ionic conductivity than lithium indium chloride, but that is only stable in the a flow of air, in the dry air. So basically we studied the halide solid electrolyte here, and the experimental data suggests that this is the crystal structure of that is a monoclinic structure, and in the structure there is a disorder is there both in the indium site. As you can see that there is 2 indium sites. So this indium 1 is there in indium 1 in this layer, and on the back side there is the indium 2, and the chlorine sites are basically on the 4 vertex of the lithium chloride octahedral unit, and this Cl2 are basically in the opposite side of the octahedral unit. Now at least if we want to do a ground state structure calculation, we have already the disorderness, so we need to do a supercell calculation, and that basically have 80 atom supercell. So conventionally, like if we want to study any absorption spectra or anything using the all electron calculation, it is quite difficult because we have already this kind of heavy element system. So now, as I mentioned that I want to study the exact spectra for this one, and this is a brief picture of that what we have in the X-ray absorption spectroscopy. So basically when we have any material, so X-ray photons comes and it taken back the core electrons, we have the scattering from the cores, and depending on the from where we have the excitation, so we see the edges different. For example, that if we have a excitation from the 1s part, then we have the k edge, and then 2s part L1 edge and L2 edge and L3 edge and so on. But the thing is that the method that we apply, we basically consider the core level spectra, so we don't have this spin orbit coupling incorporated in the core level, so we cannot have the information about L and so on. So we have only information from the k edge. So we can using this method, especially the pseudo potential method, so we can only have the information from the k level spectrum. So this is typically the absorption spectra, and mostly it is comprised of the Zen's part, that means that the edge part that is basically K, L1, L2 and so on, and then we have the X-ray absorption fine structure, that is the extended part. And so Zen's basically gives us information about the electronic property, spin state and oxidation state, especially for the battery materials the oxidation state is very important, and that has been routinely used especially for the experimental data, but there is not such strong computational information that we have, so that we can really make a hand-to-hand correspondence with the experiment. And of course these exapts basically needs a lot of core level information from the unoccupied parts as well, so that is not even available. So at present we have only information that is in the Zen's, and that is basically of the order of 50 electron volt that we can have that information. So how we implement that one in the this approach, and basically when we excite the X-ray photon from the core level electron, so so if we leave the electron, then we have a core here, so that means it's a positively charged. So this is a first initial state, and then this is the initial state, and this electron basically go to the lowest part of the unoccupied level, so that is the final state. Now the thing is, because of this one we have a all the electrons are here, so there is a core positively charged, so there will be a charge effect, and for that reason basically we need to consider the supercell kind of concept, because these as a due to the positive charge of the core hole, so we have a image charge effect, so we need to have a really big supercell kind of calculations. Another thing is because of the electron on the most lowest part of the unoccupied level, that is basically a conduction band. So due to this presence, so these orbitals will be like there will be shifting, and also the core levels, because of that one the core levels will also have the orbitals will be shifted. Now because of these two effects, then we, especially for the metallic system, this does not have much effect, but for the especially semiconductor and insulator, it has a very long effect, a substantial effect. So that's why this is very much serious problem, and using for that reason basically we need to consider that not only the excited electron core hole, but also the full core hole relaxation. So that means basically we consider here that there will be a negatively charge of the background, and then we consider only the electron on the final state. And of course, so what we do basically to understand the absorption spectra, we consider the transmittance for the dielectric imaginary part of the dielectric constant using the Fermi golden rule, and we consider only the most lowest part of the valence band and the conduction band, that one. So and we consider the dipole moment operator that is acting on, and using the basically the power potentials what we have the frozen core approximations. So basically we just need to consider both the orbitals that I mentioned, and that is the energy difference that we have in the from the band structure calculation or density of state calculation. And of course we are doing everything in the density functional theory based approach. Sorry. So that I mentioned that basically there is two method. Actually both XCH and FCH is integrated in the same method, and there is another method that is basically solving the BSE equation, but that is very time consuming, so we don't consider that one. So here what we do basically what I say that already I mentioned that we have the if we don't consider the background charge of the core, then we have the shifting of the because of the presence of the electron on the conduction band, so the shift is very huge. So sometimes it becomes very much prominent, for example lithium chloride, lithium iodide, but that need to be investigated whether this method or this method is applicable and which gives the best result as per the experimental data. So this one basically we can see here that FCH and XCH that we study, that does not show very much effect on our system. Only we have a small shift in the pre-H structure, but already this black one, that is the experimental data, already it has a spread because of the Gaussian width, and really it is difficult whether this FCH or XCH is better or which one is performing better than each other. But anyway, so basically what we see that that our both approach gives the at least mimicking the experimental data, and what we see that there are 7 features, that is the bending that we see here, and computationally we could identify the which spectrum basically mostly contribute to the experimental data. As we can see that mostly that the 4i, that means the electrons from the 4i state of the Cl, this is a CLKH spectrum that is contributing to the overall spectrum, but this 8j is not so. So this kind of informations we can get only from our computational point of view. And to understand that, basically we see that the local structure, although the Cl1 and Cl2, there are 2 sites that I have mentioned, but their local environment is not so same. For example, the Cl1 which is bonded, the lithium one, which is a bond length of 2.525 and then 2.566, but this there is a bending of the next lithium one, the coordination. So that is basically because of that one that we feel that this is the this variation, especially on the this regime, is coming because of the this local change in the coordination number. And then basically we need to understand that how it is and which spectrum is basically which part of the contributing there. So to understand that, basically we need to understand the density of state. So basically we calculate all the density of state, partial density of states of all the lithium, indium and chlorine, and we should consider the mostly the unoccupied part of all the partial density of state. So, and this is just that what we did, minutely analyze all these things, and what we understand that these 7 features basically that we have, so that this peak basically corresponds to the metal, especially the indium P to D orbital mixing, and this peak B basically originates from the chlorine S state, and then peak C and D basically admixture of these two ClPz states, because we have lot of different chlorines in the structure, and then peak E basically match with the indium Px and Py with the hybridization of ClPx and Py. So this is for the reference that we consider, but of course we have studied minutely all the partial density of state of all the atoms and their partial density of states. Now basically F also originates that due to the indium F and chlorine P state, and G also both indium and D, indium SP and D admixturing states. So again we also know that the solid electrolytes basically are metastable condition, so experimentally don't get that pure phase, so there is a glass ceramic kind of thing, and there is a presence of the defect. So we consider the system like there is a chlorine which is in a Frankel condition. From the last talk I think people have already understand there is a defects is there in the material. So what we consider like that vacancy on the chlorine side, regular side, and it goes to the chlorine interstitial side. So overall the stoichiometry is maintained and charge is balanced, and similar thing is happened for the lithium also. And also we consider the Schottky defect, that means that both lithium and chlorine, it moved from its original regular side and goes to the it is removed from its regular lithium and chlorine side and maintain the charge balance. So what we see here basically that for both cases we have in a higher energy value we have small shift there, and that we checked minutely and found that basically the although the pristine nature is maintained, but there is a blue kind of shift. And for lithium Frankel defect, the main peak splitting is between C and D, as we have mentioned earlier, this regime, basically this regime, and the CLK spectra originally 8J and 4J. So there is a change in the coordination number after we introduce in the defect that we have found here, and this and the states basically for this one Frankel this one basically due to the indium D state and chlorine S states. So this also we extend the idea for the chlorine, not only chlorine but for the indium case also, and there we find that the experimental data, and also we compare with the indium foil and indium oxide that is available in the literature, because in the system we should have the lithium indium in the +3 state, and we find that at least the first peak basically matching with our spectrum, and that basically corresponds that the indium in the +3 state in our system, and basically we see that that KH for both cases like the 2A and 4G, but there is not much difference, only C and C prime that we have mentioned here, there is a small shift, and mostly we have see the transition because of the 1s to 5p in the indium state, that is basically responsible for the spectral origin. And also we want to extend our study to the for the interface, because in these materials are used in the battery, and we have the basically lithium as a anode is used in the lithium-ion battery, but literature shows that experimental data shows that the lithium and lithium indium chloride is a reactive interface, and there is a formation of the indium lithium chloride, and so we want to study the interface, and since this is very challenging work, because lithium what we have in the system like that this is the -2 -3 -2 peak is most highly intense, but we don't have any evidence that whether really this is the most prominent peak or not from the other source, but we consider this one, and we have the we try to make an interface with this Li3InCl6 with -2, -3, -2 plane. Along with we took the lithium. This is a interface that we have the after structural relaxation, and we already find there is a lithium and chlorine makes a bonding, and it has the lithium chloride formation of lithium chloride is there, and we find that this is a reactive interface and there is a bulk like nature, and we study the excitations from the chlorine from both sides, and we could see there is this red one basically comes from the this bulk like nature, and this one basically corresponds to this spectrum. And so we understand that in the bulk like nature we don't have much deviation, but it does not really one-to-one match with the experimental data, but we don't have any interfacial kind of data, only we have the data from the pure kind of samples. But we saw that there is a significance in the deviation in the chlorine spectrum as we have from the interface. Yeah, so in summary that we have implemented, that was in VASP, so we use that both XCH and FCH, and we find the XCH is quite informative to reproduce the experimental data, although we could give more deeper analysis, and that only spectral features coming from chlorine side rather than indium side, and there is a significant peak shift in the chlorine in the interfacial part. So yeah, so the computational facilities used from the ISAR Pune, and Biplav is there, so we have used his facility and the ACRB SRG grant that I have, and thank you for your attention.
Thanks, Tanmay, for finishing in time. Questions?
Very nice talk, Tanmay. I was curious about this because you show that you talked about the core hole valence electron interaction. In your theory, that interaction is neglected. So, so do you think that this class of materials can be simply treated by your method of doing like these kind of calculations, or you need to go to many-body physics?
If we can do the many-body, solving the BSE equation, that's the many-body perturbation theory, that definitely give the better answer, but at least we show here that the experimental data what we have both from indium and chlorine matching with our these first-hand approximations. So because getting the exact spectra for the 80 atom cell, already we have feel the pain, so it's very difficult.
If there are no more questions, so let's thank the speaker.